was very happy to talk in this 41001 in connection to the Extreme 2ED grant. So for those who have been in my class, I have no problem with my accent, I hope. For those who are new, so I have some Chinese accent, so hopefully it will not hinder the communication. All right. So what I want to do today is to tell you some old and new research problem in matrix theory, but not limited to the matrix theory. So as the grant indicated, we want to handle large data sets. So I will try to connect matrix theory and some recent study. You can see what tensor, you will see it's just an extension of matrix and helping us to do managing large set of data. Okay, I will impose on some additional thing. Everyone have 211, right? At least. Good. Okay, so start from there. Some have 4, even better. Oh, okay. So no padding is okay. So what is a matrix? So if we have taken 211, if you tell people what is a matrix, it's directly related to data, right? It is just an array of numbers. Numbers are data, right? You picture everything, you can digitize it. So you can use number, 0, 1, just 0, 1 sequence to represent any picture, any English, transform into certain 0, 1 string. Spell checking is just comparing two 0, 1 sequence, whether they are the same, they match. If it doesn't match in any dictionary word, and that is not a word until you invent one, right? So data is just just number, and if we arrange them in an array, a rectangular array, m row, n column, so that will be a matrix. Everyone agree? Okay. Okay, so for example, I mentioned that this is just data. You can initiate 1, 2, 3, 4 all the way, a long vector sequence, like in 214 or in taken 311. So we talk about sequence. But here we have for some reason, sometimes it is convenient to write in this rectangular array form. Okay, and of course you have seen application or calculation in 211. You know this makes sense. And I give you more motivation for that. This is a very old application in some sense, but good enough to illustrate that in certain circumstances, you would like to arrange the data in rectangular array form, and then it actually represents more than just the numbers. For example, in the olden days, suppose you only have a black and white picture, and so one way to digitize it is to look at the picture frame, and you only have black and white, but still you can have different degree of darkness, right? So you put a number at this particular pixel, you make it darker, so 10 degrees, for example, of darkness. And then in some place you want it to be white, and you get 0. So as simple as 0 to 10, you can produce a black and white picture which shows you something. True? Now you can, like I teach linear algebra, you always think about simple K 2 by 2, 2 by 3 matrix, but you can think back. If you have good enough machine, you can do color encoding. Some color represent, some number represent some color, some how bright, how red, how green, how yellow is the picture, right? So again, it's a whole bunch of data. You can then record a colorful picture. Okay, so let us not to make it move. Nowadays we talk about movie, of course, right? So later we'll talk about how to encode movie using data. Just this one. So using the simple-minded idea, we can encode this picture using a bunch of 0 to 1. Depending on the darkness. And then you can transmit and store this picture. You store this number. Next time when you bring up this data, again, you can reproduce the picture. If I want to send my picture to another friend using email, then I send the matrix containing 0 to 10, for example. Okay? So that is one occasion that you might want to, the physical representation of the object. You want to use a rectangular array of data to represent it. Okay, so what can we do about this data? If we have infinite amount of resource, you can make it as accurate as possible. Try to find the pixel or decompose the whole picture into many different very fine grid, and using many different levels of color, black and white to represent it. But maybe you have a limited amount of storage. For various reasons, when you talk about really big data in reality, you may not have all those resources. So can we do some trick about that? Think about easy transmission, easy storage. Okay, so we want to achieve the same effect or similar effect using much less storage. So that is exactly the hot topic of data compression nowadays. so much data. Every day you receive data from outer space. Check whether there are some extraterrestrial or any activities out in outer space. You transmit email every day. The volume of data transmission is huge. So data compression, how to make an efficient way to compress data and therefore easy to transmit is very important. Okay, so we have some trick. So for white people will be happy. 211 students, we skip the last 2 chapters, and some people like Greg came to my other research class here 100 times that one trick we use is called a singular value decomposition. Doesn't matter. I just accept it. You just accept this fact. And if you are interested, you can look into that. Very easy in your standard linear algebra book. For real matrix, you can do that. There are some versions of complex matrix. So what it does in your study is very weird. The instructor said that, oh, every matrix there is a good decomposition. How good? Okay, so you can have any square matrix in this case. You can always find a orthogonal matrix. Remember, orthogonal matrix is those X transpose X equal to identity. The nicest kind of matrix to find in this, right? You may remember at the end of 211 course, usually we talk about a orthogonal matrix. A whole bunch of orthogonal matrices which satisfy. In particular, I put it in this column form. You know there are many equivalent forms. So X is orthogonal simply means that the inverse is the transpose. We'll use capital T, small t sometimes. And of course, we have this one. But the important thing is that this column so-called form a orthonormal basis. Length 1 and orthogonal to each other. Inner product is 0. Remember the inner product? You can have 2 vector X and Y. The inner product will be just X transpose Y. That is called the inner product of the 2 vectors in our N. Okay, so make your life tough when you study this. We said that, okay, there's certain form, right? You diagonalize a matrix using similarity, you do all kinds of tricks to matrix. One of the tricks is called singular value decomposition, which says that you can always, no matter what matrix A you have, you can always find a orthogonal matrix X on the left-hand side. I intentionally write in the Y form, okay? So you can imagine that if X is in this form, so X S1 up to Sn, Y transpose, because I write in this form, so this will be Xn. Y1 transpose. When you do the transpose, you use the first column take the transpose, second column take the transpose. Block matrix multiplication. Some of you may have seen this in 211 or any before, right? So if you do block multiplication, it is the form I wrote over there. It turns out that this is a long vector multiplied thin guy plus S2, same thing. Okay? So that you can use block multiplication to represent in this way. So, and then this is saving it for later use. So I talk about tensor. One way to understand this X1Y1 transpose is some people use this notation. Okay? And I'll tell you why we need that. Okay, so if you do your homework and the professor said, you can always do that. Why do we even want to do that? If I use the motivation that you want to record the matrix, the n square entry, right? N by n matrix, you have n square real entry to represent your picture. What the heck, why are we going to use n number, n square number to represent this n square data? It doesn't make sense. True? Why in the world would we make the situation more complicated? We already complain using n square data is difficult. And now I'm asking you, oh no, do it in this way. You use more data to represent the matrix. So, what is going on here? So it turns out that there's a trick and there's some special thing we can take advantage of. Number one, if the data have some structure by itself. So everyone knows the rank of the matrix, right? So you reduce to row echelon form, see how many pivot in one, column, row, and so forth. The fact is, if your matrix is rank R, or rank K, then many of this guy is 0. So you have fewer number. Not only you only keep this K number, but all those other columns are useless because when you write the representation, you only need up to, remember, the thin guy, and then you can stop at SK, this one. let me tell you an extreme case. If it is rank 1, how many data do I need to represent this matrix A? So I only need one guy, one data, n data, n data, 4n plus 1 data. Tell you everything about the matrix. Hey, you do any elementary calculation, you know that when n is 1,000, 2,000, exceeding that, of course, we are getting a large data set. See how significant is the saving. Okay, if it is true, it's not too bad. Still, I can use n plus 2. I capture everything. Right? So that is number one. If the thing itself has rank k, then this representation is far better. So when you need to send an email, send n squared data versus 2 plus 4n data, it's much, much faster. Even transmitting a movie, right? Many, many pictures. So that is better thinking. But in reality, life is not so good. You do not imagine that always you have a picture, a matrix represent, it can express low rank. But here is a philosophical question about large data set. So there are no official, I think I can say, definition of large data set. How large is large, right? Today, large data set is something of that order. Tomorrow, better machine, you can handle other large data set, right? So the study large data set is to study the impossible. Some people say that whatever the current technology cannot study those are large data set. So there's no end for the storage, right? So suppose I need to handle n squared data. But my machine, I mean, in 211, I can only do 4 by 4 matrix in class 5 by 5, not only killing the student, but killing myself also. What do I do? Homework, we are stuck there. For some given program, maybe the choice is to stop there. But for research, actually, the idea is the following. If I have a large data set that the current machine cannot handle, but how well can I handle that? How well can I approximate that? Right? We try our best. Many things in our life we cannot completely control, right? But we try our best to achieve the best result. So if the thing is rank 100, but I can only handle rank 90. So what? So what I would do is that I truncate, take away all those additional things. Yes, I know 90 is not quite 100 rank, but that's all I can handle. So I use only 90 of them to approximate. Hopefully it is close to that given picture. Error, I know, I admit, because I have limited resource, I cannot handle everything. But with this 90 rank thing to approximate the 100 rank is better than just stop there, do nothing. True? So under that idea, not only you can handle a rank K matrix, if it is higher rank, depending on our resource. Today my machine can handle 90, I do 90. Tomorrow hopefully I can do 100. But of course the data will also become larger and larger. We keep chasing it. But as researcher, optimize the thing, we try our best. Okay, so the idea is to do approximation. So as I said, you can only do R. Okay, you're not getting A. You're not getting the same picture. But hopefully in the theory show that if there's some, you can predict how bad the approximation is or how good the approximation is, right? For some problem, actually, it doesn't matter. My TV at home is like 20 years ago. You give me the full picture, I would not be able to appreciate that. That approximation with my no eyeglass or glass or something, that is good enough. Then that is good enough. In some problem, the precision has some allowance. Then you can use a low-rank guy to approximate the real guy, even though that is not completely accurate. Now, the problem depends on your application, right? In a medical application, you don't want to make it too far off, otherwise you're killing people, right? In surgery, that you cut, instead of cutting part of each tooth, you cut the whole organ out, and end of story, right? So you must know what is the tolerance, but still, the idea of try your best, given limited resource, what can you do? If you do your best using your current technology up to rank R, you cannot do anything meaningful, then we have to find other way. We have to improve the hardware, improve the storage, right? So that is the kinds of thinking driven that. Number one, we want this tool can handle everything. If not, what is the best we can do? Can we then, given the limited resource, can we do the best to handle the impossible large set of data? Make sense? Still okay? So that is the kinds of thing. So what can we help to do? I mean, even undergraduate or graduate research. Okay. So one recent result about this is the following. In physical device, we may be able to, well, we have to transform the data set one way or the other, storage or whatever. So we talk about using this singular value decomposition, doing all these calculations. But perhaps in some application, the data set is going through some transformation. How can we preserve the integrity of the data? How well can we preserve the data? In our application, if we make sure that the first R singular value are not changed, so that the picture has reasonable quality, what kinds of transformation do that? So that is one of the items, besides finding good way to represent data, is the change of data. What kinds of changes we can make to the data without changing the objective, the representation of the picture, or can we simplify, actually using some transformation to make the thing simple so that we can easily find the singular value decomposition or store the data. Okay, so it's many related questions. So some recent result that people object, right? Many of you were not even born in 1990 reason. I'll tell you why this is recent result later, justify that. But anyway, not so recent, okay, in 90. So my friend and I not even considering this particular application. We say that, okay, so if indeed we apply a linear transformation, so that is the thing you know, right? So if you, for matrix, linear transformation will be if you apply it to two matrices, then the effect should be the same as applying individual matrix and then add them. And then for any real number, you multiply the matrix A, after you apply the transformation, you get this. Okay, so if you look at a data set represented as matrix, very natural question. Numerically, and also later I tell you some application, it's natural to consider linear transformation, linear map. So what kinds of linear transformation will not change the singular value? I put A, I put DA, always at the same singular value. Let me not worry about, remember the singular value decomposition, which tell you how to reconstruct the picture if you think about that application. So here, let us not worry about the X and Y, just worry about this important data, which tell you something about the picture. I don't want it to be changed. If we change it, we change completely, perhaps very messy, the resulting picture. But sometimes I don't care about all the singular value, right? I only care about the first K of them, first R of them. And actually, as strong as I only care about one of them, if I want to keep one of them up to that threshold, nothing changes. And that particular guy doesn't change. I don't care about the other. So maybe that is enough to guarantee some quality of your data not being transformed. So what kinds of transformation will do the job? So actually, there is a more general theorem. A simple particular version in this context is that it turns out that all you can do about the picture is that if you derive a mechanism, a machine to change the set of data, you better make sure if you want to keep the singular value unchanged, or if you want to keep one of the singular value unchanged, the largest one, the smallest one, the middle one, I don't care. As long as you insist one of the singular value is not changed, the only hope is to apply what we call equivalence. So we just left and right multiply by a fixed pair of orthogonal matrix. That is one possibility. Another possibility is that your transformation can only change A to taking the transpose, and then PA transpose Q. Does it make sense? So anyone who want to do data, want to do transformation in physics lab, doing whatever experiment, and you have some laser beam and also electromagnetic field or whatever, to change certain thing. The certain thing can be recorded as a matrix eventually, and you do not want to change the invariant, what we call a singular value. You better make sure your equipment corresponding to a transformation using left and right multiplication by orthogonal matrix. Otherwise, you're out of luck. You will change some of the singular value. If it is very important, then you may be in trouble. So that is the meaning of this result. Yes, correct.
So does the third point apply when if you have to do multiple transformations, if you keep multiplying on each side by orthogonal matrices?
That's correct. So, but it go to group theory. If you have go to 307, if you do multiple steps, you can combine all of them. You can use one single one.
Okay.
Right. So even though exactly in experiment you do multiple steps, if you do many times of this, you get this. Many times of this, you get this. If you mix these two guys, you land at one of this. You can eventually find one thing to do the whole job. Very good question, actually. you can imagine now, you have to check with applied people to see whether such a scenario could arise. Indeed, if you apply your whole process, can go through many transmissions. Somehow you want to simplify the transformation. Instead of going from station 1 William Mary, go to Brown, go to Princeton, who knows. After several rounds, keeping the picture intact. But I say, oh, I suddenly build a channel, like I can go to Princeton, which means that I bypass all these different steps. But if I knew every step is done by this, then I know I can find one single R and S directly send it to Princeton. Okay? So yes, very good. So not only superficially there's a result, but you can ask many related questions. What happened in a applied scenario or even in a theoretical situation? Other questions? Good.
So
Okay.
this case singular value, that means that the SK.
Right. We always, there's a convention in matrix theory, we always assume, because singular value are not
Yeah.
you can always arrange descending order. So the largest singular value.
Okay. But the first conclusion is each singular
Yes.
value. So,
It preserves each one is the same. If you want to preserve each of them, you only need to check one. If you want to preserve one of them, it will preserve all of them. The magic is. For example, you insist the largest singular value unchanged, then it must be of this form. Of this form, it will automatically guarantee all singular value will be unchanged. Right. So depending on how you use this result, in some sense it's very restrictive. You want to keep the k guy, the largest guy or the smallest guy, for example, from 1 to 100. My picture only care about the 51. I want to make sure the 51 doesn't change. But it already tells you that the only transformation is this kind, which means that all the singular value will not be changed. Okay, good news and bad news. Depending on how you use it, right? Good news is that the structure is extremely beautiful. One good thing happened, all the good things happen. That is the good news, right? The bad news is that, oh, I only care about the 50. I want to have more transformation. I can do the change. But the result tells you that no. Even though you only want to keep this guy, you care about this guy, but you better make sure every guy is being preserved. More discussion or questions? Okay, so this is some known result. So you don't agree this is reason. Okay. In application, often case we do complex matrix, we have a similar result. So if you are interested, there will also be corresponding result, exactly the same thing, corresponding singular value decomposition, corresponding singular value, corresponding theorem, like that, except that this becomes unitary matrix. If you know what is the meaning of unitary matrix, which is just those complex matrix. U star would be you take every entry, you take the complex conjugate transpose. Unitary matrix are U star, U star. It's a complex analog of the real case. Everything, the whole set of theory can live today. Right? But for our presentation today, you can focus on real matrix for the moment. Later, I will stop some complex matrix thing there. So this is the 1990 paper. And after I joined William Mary 2 years, so now you can guess my age anyway. So after I arrived here, so this is the paper published at that time. Why reason? Result to me is always reason, because compared with the old result for Binius, famous mathematician, it's 1897. Now it's like 2 centuries ago. So this is now 19th century, now it's 21st century. So the first paper of this kind of study is something you know determinant, right? So they work on complex matrix. What kinds of linear transformation will not change the determinant? Of course, determinant, is very important, right? Whether the matrix is invertible, whether a system is always solvable, unique solution, everything 20 conditions reduced to this single number, determinant of A. Okay? In application, maybe this determinant also measures something. In geometry, it is the volume of some geometrical figure, the determinant of certain parallel pipe, and then you can extend the determinant idea to ellipsoid and so forth. You can use the determinant to help compute the corresponding geometrical object. In some physics and chemistry application, if you look at the matrix model, determinant will measure certain kinds of energy. Okay? So this says that if I don't want that thing to be changed, what can happen? Turn out that it is a fun exercise, you know all the terminology. It is easy to check I can easily put it in 211 exam and figure, right? So, but if I put it in 211 exam, I have a transformation left and right multiplied by two selected matrix MN, then that will be linear. MAN, and then you do MN on left hand side, right hand side, you see that these two things will be satisfied. If I choose determinant MN equal to 1, I guarantee that before you transform, after you transform, you get the same determinant. Okay? Because I'm using the fact that determinant xy is the same as determinant x times determinant y. Go check it. This will ensure that that is the case. Transposition will not change the determinant. So these are obviously linear transformation will not change the determinant function. The contribution or the big thing about covariance is that the converse is true. If you look at a linear transformation preserving this energy, this volume, whatever this invariant mean, determinant, not changing it, then you must be able to find a pair of AB to do this job. So graphs come and also come back. If you do it many rounds, again you can combine all the things. Eventually the final thing will be of this form. Okay, I don't know how much you know into the May famous algebras. Also consider this a little bit later. More recent than this one, still last century, 1949. So proven that, what if you have a invertible, the map is invertible, non-singular, have an inverse, this as a function, as an inverse, for those in 214, you know that, or for linear transformation as a matrix, and you know the inverse exists. So for such a map, if it sends singular matrices to singular matrices, those guys with determinant 0, you can imagine in the previous century, these are big issue determinant. Matrix, 0 or not 0. Anyway, very interesting. The result is very similar. You only need to find two invertible or non-singular matrices making the same form. Then it will guarantee that the matrix, the transformation will be non-singular and send singular matrix to singular matrix. Okay. All right. So some of you may be interested in pure mathematical study. This is interesting statement, regardless of the application, but just to demonstrate that that's known as the preserved transformation of matrices, some problem. There are tons of problems, over thousands of papers. You can look at this, for example, survey in AM Monthly, Stan Pearson and I wrote in survey on that. Easily get, you can search and then see the long history from whatever hill and applied reason. People consider transformation in matrices. And over 1,000, easily even 2,000 papers you can find. Last even last 2-3 decades. I mean, there are many papers on this subject. Okay, but let us not too far away. Go back to our project. It's about large data set. So go to tensor. So now, quickly we move into, for a two-dimensional matrix, we say that you can write as this thin guy, this guy. And I give a notation saying that this guy sometimes people write x1 tensor. That one is simple. x1 tensor y1. Okay. And this is exactly where it allows us to do the extension to tensor. So matrix is just a order 2 tensor. What I can do is to stack the matrix. Well, starting to 11, double index matrix is horrible enough, but I'm telling you that now you have to look at triple index. But that is extremely natural. And you have, how many of you have seen 3-dimensional things? Have you played with those 3-dimensional things? How does it work? Have you seen how it function? Yeah. Yes. It's very simple. Let me suppress K. So if I do 1,000 layers of the same thing, so first of all I do a matrix and draw this picture, or put a layer of stuff there. And then ij, so of course you have two ij from 1 up to m, j from 1 up to n, right? The second layer k equal to 2, you spray another layer, another layer, another layer, another layer, and you get a 3-dimensional object. So that is as simple as that. Movie is just a 3-dimensional presentation of the picture, right? So you have a stack of pictures. When I was a kid, I don't even have those movies. You draw a bunch of pictures and then you just, have you played those games? A bunch of paper, right? Then you quickly move one paper to another paper and then you see how does it work. So I draw this, right? You draw the thing here and then you and then you can see the thing seems moving, right? Nothing new. 4-dimension tensor. So I restrict to 3-dimension tensor hypermatrix. But can you imagine a scenario of 4-dimension tensor? Do you want to take the leap of technology? Game? Video game? Video games, look at this. And then the screen, time change, right? The future, who would play these kinds of 2-dimensional game? Of course, it's the virtual reality, right? 3-dimension in this room, I'm fighting with my whatever, the master fighting with people. And this is time dimension, right? I produce this 3-dimensional image, I'm fighting for whatever monster to save the princess, and then as time goes by, I have the next frame, next frame, next frame. Then you would have AIJK representing the 3-dimensional space, create the environment like your scanning thing, not scanning thing. The virtual reality will put the 3-dimensional environment, the 3-dimensional matrix. You need the other one, T-dimension, to create your game. Okay? So, any computer scientists or science people? Next generation, right? You will take your lead from a company to do this virtual reality 4-dimension game. Okay. Even in this very short presentation, then we have one tool which is called the singular value decomposition, which allows us to make a complicated picture into a simple picture or a simple approximation so that we can do things efficiently. It's the idea which works, right? So can we do tensor? Okay, so think a little bit about that. What does it mean by decomposing it into one tensor? So the simple situation, first of all, I want to write this 3-dimensional object. Imagine, right, okay, so into S1 and then 3 factor. So you think a little bit beyond matrix. Why the rank 1 guy, this thin guy, multiply this guy is simple. As a matrix, you see n square entries, right? But actually, it only depends on U1, U2. Probably should not use that. What's the good notation? L1, L2, L3, for example. Left and right. When you make a mass, multiply L1, R1, and so forth, you see 3 times 4, 12 data, right? But if you're smart enough to recognize that this is just a rank 1 matrix, then you're using 3 numbers to multiply this 4 number. That is a distinction, right? So 12 data is really depending on 3 data and 4 data. 3 plus 4 data is enough to record everything. This 3-dimensional thing is no different. If I give you a hypermatrix, 3-dimension, 4-dimension is your base picture. You allow 5 time unit. So you stack 5 pictures together. How many data do you need? 12. 12 for each picture, and then 5 pictures stack it. 60, okay? But if I tell you that this box of data, this hypermatrix is actually rank 1, quote unquote, what does it mean? I can use 3. To do the basic picture. So let me, I don't have a 3rd dimension to draw this kind of thing, so I use the tensor. Now you see why I use the tensor notation. This becomes friendly. So if you do the translation, this is just the base picture, 3 by 4, 12 data. And then I have 5 units, right? So time 1, time 2, time 3, time 4, time 5, to represent the 5 picture. How many data am I talking about? It's 3 plus 4 plus 5. True? So I describe the whole thing. If I'm lucky enough, that whole box of data is actually the same picture, but scaled by T1, T2, T3, T4, T5 as time progresses. So that is much, much smaller size data. Exactly the same as singular value decomposition. What if it's not 1 but 2? Still, the amount of data is much, much smaller. So people are interested in saying that how to recognize something is U tensor V tensor W. That is relatively easy. You can go home and try. I give you 60 data. Can you find 3 factors so that those data are represented this way? By the way, if you write down the 3-dimensional matrix, you always use U1, UI to multiply Vj and Vk. That's what happens. I give you 60 data. Of course, this eventually is just 60 numbers. you know one number corresponding to 111 position, so you use this to help you to figure out what is the position of that data. But you can ask, hey, can I find vector like this? It's relatively easy to check whether one guy is a rank 1 tensor. But the big challenge is an open problem. How to write it in 2 of them, 3 of them, 10 of them. Why do we want to do that? Remember, if I recognize that this huge amount of data can be represented in this way, so the number of data only is mn, I use k, but mn key data roughly for each one, and if you have r of them, you just r multiply that. At most, you get S1 up to SR r more down. It's much, much more efficient. It's serious. It's very serious research. I was in a conference in December in China. The whole conference is about tensor. That is one of the important problems. It's unsolved. And has many applications with additional structure. Can you write in this form? Well, recognize it so that you can store information easily. What is the next step? My old comment, right? Even if it were not, you make it like rank R, right? So if the approximation is good enough, I throw away many of them. If I can make it 100, but I can only have storage for 90, so I hope that 90 is good enough. No, tough luck, then I have to go back to the hardware to improve my storage, right? But if 90 is good enough, so today I can already handle that huge data set, even though I don't have all the memory in the world to keep that 100 rank 1 tensor. I keep 90 of them. Right? But for sure, it is proven that there's no corresponding result like singular value decomposition. You cannot find orthogonal. You see, what it meant is that you find orthonormal basis x1 up to xn, y1 up to yn, and write it in this 2 tensor form, the singular value decomposition. For this one, it is provable. You can prove that actually. Find some examples showing that there's no hope. Almost trivially, you make up some dimension. There's no hope to represent things like U1, U2, U3 up to UR orthogonal, V1 up to VR orthogonal, W1 up to WR orthogonal to represent the data. No hope. We need new idea to deal with it. What is the new idea? What is a good idea? If you can do that, you see, think a little bit about the very geometrical way the singular value decomposition works. If I can write a matrix as S1, the thin guy, this 2 tensor, 2 tensor, 2 tensor, it means that I revolutionized photocopying. I copy the 3-dimensional thing, the 2-dimensional thing, the same thing. You guys are too young. You have not experienced the age when I was looking at the dot matrix printer. So I look at the printer. Do we still have dot matrix printer nowadays? Sometimes. But at least it's 9 by 9, right? Even laser, you see half of the page come out, so it's 9 by 9, right? But this completely changed the game. This says that you use a rank 1. I think it is actually, I don't know how well this idea can materialize, right? But think about the singular value decomposition. I'm telling you that, first of all, assume you have a transparency here. Instead of 9 by 9, I do the thing. I first of all produce S1, XY, a very simple picture, for the rank 1 matrix. And I spray another layer using S2. I spray another layer. Instead of doing this linear way, step by step, I can do the photocopying in this way. Now, mechanically, it's very difficult because the mechanical thing is always line by line. You go through the copier or you go through the copy machine. That is the situation. But 3-dimensional game, if you are serious in taking the lead of doing virtual reality to do 3-dimensional game, I have all this sensor here and all this light here. I do the rank 1 tensor. Boom, I show the light, and there's the environment. Extremely bad approximation. You want to create a forest situation, a fortress to help the princess. Maybe you only get some dot the first round when you project all those, right? But if you project another one, it's no longer you create an environment, right? Layer by layer. You get just like zoom in, clearer and clearer you have the 3-dimensional reality to play with, right? So, of course, that has to work with the engineering. But this idea is unlimited when you think about that, as simple as that. But the first thing we have to overcome is this tensor decomposition. And you can start from small. 3, 4, 5, yes, laughable. In 211, 3 by 3 matrix, 2 by 2 matrix. But we develop the theory, and we go anyway. All right, so that is this tensor situation. And as I said, you can think about 4-dimensional tensor, which means that a 3-dimensional tensor at the time thing. 5-dimensional tensor, I cannot give you any good idea how to visualize this, but it is useful. Any structure you can extract from the large set of data, you almost make it like this. This kind of thing will be useful. Of course, the arc is that I give you a whole bunch of data from statistics from the real experiment. How do you recognize that? How many layers? How many tensor? How many order do you do that? The picture is clear, but usually you are handed a whole bunch of data. And actually, as I said, in December I was in a meeting, the brain scan, you get all this data, they actually group them together so that it fits into this mode. Mathematicians sometimes do artificial things to help the real problem. The given data, number one, there may be some hidden structure. You want to discover that. Sometimes there may not be hidden structure. There's no structure. But then you try to make some structure out of it so that you can use to study that. So that is another aspect. Okay. So you say, like me, sometimes, how it is an art. So it is hard to decide this data set can be decomposed as 3-order tensor, 4-order tensor. But luckily, people like me so straightforward, there's some natural environment that the data is presented as tensor. So some of you know that I'm interested in quantum computing, so that is a situation. Physics major or physics student, so you know in quantum mechanics you can have vector state or use the matrix to represent quantum state. So in the vector state situation, all quantum system is described by a unit vector. And very naturally, when you combine 3 systems, you have a photon here, you have, I don't know, an atom, up spin, down spin, or whatever. 3, 4 different things, for some reason, you put them together. Or even the same system, 1 photon, 2 photons, 3 photons, how do you put them together? Each of the things will have their own behavior, described by the quantum state, vector state V1. The other one is V2, the other one is V3. When you combine these 3 systems into one so-called multipartite system, in this case it's a tripartite system, right? The vector state can be easily described as the tensor. So it's good and I think it's good, right? So the question itself tells you that there's a natural tensor structure there. So it's not a choice. The earlier one I think is larger potential. You can choose how to divide the tensor, apply your technique, and make something interesting. Much tougher, in my opinion. I mean, you require good insight to see those things. This one is natural. I give you 3 systems, and then you have 3 vector tensor. If in quantum mechanics, you know that if I do not do anything, which is impossible, you set up the quantum system, it will be affected by the external environment. Again, you will be rich if you can control the tensor state, the quantum state doesn't change in a split second. In millisecond, it doesn't change. It will be great help to quantum computing. It keeps changing because in all the environment, there are some quantum effects affecting this vector state. So quickly, it becomes a mess. A mess meaning what? I have a 3-dimensional quantum state, a 4-dimensional, what's this one? 3-dimensional quantum state, 4-dimensional quantum state, a 5-dimensional quantum state. I put them together in my lab. So it is in this form when I put them together, the tensor state. But after 1 second, 1/10 of a second, the quantum state is no longer in this form. It is just a single tensor of length 1, 3, 4, 5 is a 60, length 60 unit vector. All you see is the 60 data, maximum element. And you can imagine that if we cannot identify it as a tensor, at least we want to say that how close it is to a tensor or to a combination of tensors. So we certainly consider the decomposition I mentioned earlier. So it's the nature of the problem asks for this decomposition. It's not that just we invent this notion. Okay? So there are, I mean, as simple as 3, 4, 5. I don't care whatever means, computer, paper, pencil, algebra, analysis, whatever topology class you take, computer science. Think how can we write a 60 data, group them, label according to IJK, so that they can be written as S1, U1, V1, W1, and so on and so forth. That is already the first exercise I can do. Or even 2, 2, 2, a 8 vector. just link big data, right? Two data, really tiny small box of data, right? Two. How to do that? It's an efficient way to do that. And then, once you know how to do that, you will find the best way for our purpose, approximation, and so on and so forth. Okay, so here is maybe a difficult, somewhat difficult for some of you, but if you understand the basic idea of these three tensors, so I can also organize matrix. So that is quite terrible. Already I said 2-index matrix is tough, and then we talk about hypermatrix, and I can talk about 4-index matrix. But I think in quantum computing, very often we deal with something called density matrix. So this is a square matrix, positive semi-definite trace 1, whatever it meant. Again, the tensor structure comes automatically. In that case, the tensor structure is like that. If you have for example, a 2x2 matrix, so the A11, A12, A21. Oh, by the way, quantum computing is all about square matrix, but stack many of them together. That's what called one quantum bit, 1 2-bit. So you tensor another one, maybe it is already 16 by 16. This is already 4 qubit grouped together. So there's a little C here. So the tensor product is very simple. You just make copy, like A11. Is it okay? After you get this one, of course you can further tensor with a C11, and then you can keep making it larger and larger. Every step, you increase the dimension by that same number, right? 2 by 2, you double the size. If you tensor by 3 by 3, you triple the size. Row and column. So altogether, you have 9 copies, right? You have a 2 by 2, you make 4 copies. 3 by 3, you have 9 copies. So it grows really fast, really fast. Is it a large data set? Yes, of course. 2 to the power 100. Who in the world can handle that, to store those data? Okay, if you cannot store those data, what's the trick? If nothing else, today I repeat 10 times, you do the decomposition trick, right? And again, it turned out that it is not just an analog of what we did for singular value decomposition or free tensor. In quantum computing, quantum information science, this is a big issue. How to decide whether you can write, as I said, if you have a bipartite system, you just compose A1, B1. 2 by 2, 2 by 2, just 4 by 4. Think small, think big in future. Now work on small example. If I give you A1, B1, it is very easy to detect. I give you a 4 by 4 matrix. Okay, so you cut it into this. Is it possible to write into this? How would you do? How would you instruct a program to do that, or by eyeballing it? How can you tell it is like this one? Of course, you look at this piece and this piece. If something like this can happen, these two pieces must be what? Multiple of each other, right? A11B, A12B. You look at the 4 number. These 4 numbers, they may be all different, but they should be of the same ratio. Likewise, going down here, same ratio. Going down here, same ratio. Detecting one guy is in the rank 1 situation is very easy. Our challenge is whether we can find a so-called convex combination. Simply means that suppose I have matrix trace 1, then if there is a combination, I want the combination to have some special feature. That is related to the early discussion. How to decompose it? When you can decompose it, then we ask for special feature to help our problem. In quantum computing, it is extremely natural, very simple for a 4 by 4. If it is not itself A1 tensor B1, can you find T1, T2, T3, T4? As many as you like, finally many. So that it is a so-called convex combination. It simply means that I take positive number, add up to 1. People study probability know that this is just a probability distribution, right? So that it is A1 tensor B1. Can you do that? It is open for general. And 2 by 2, 4 by 4, there are some easy way to check that, but otherwise, very difficult. And it's very useful, important product. Yeah, so again, if you're interested, you can try anything. If you get any idea how to do in special way, even for low dimension, who knows? Maybe we can extend it to the general situation. For computer science students, actually, for large size, large data problem, this is an NP hard problem, so to speak. So finding an easy computational algorithm will be difficult. And the question reduced to, for a special class, can we have a special technique? My earlier philosophy, right? When you have large data set, you don't have enough hardware to deal with it, you try your best, right? When you have a result, you know that computationally there will be no uniform result doing this decomposition. You ask the question, suppose I know a little bit more about C, some structure. So in your application in quantum computing, maybe you have to deal with these kinds of quantum state. For these kinds of quantum state, can I do that? You can always ask that. But at the beginning, you can just try 4x4 or 3/4, which is 12x12, and do it in M3 and M4. So the same line of study, okay, this is more recent result. Actually, we ask the same question. Suppose we want to, again, mathematics, how to do a problem like that. It is difficult to recognize whether it can be decomposed into certain form, right? And if yes, then you decompose it. The question actually is whether you can do that. After you can do that, then how to do that? These are the two-step question. So we want to apply some transformation to change the problem. You give me a 4x4 matrix. Can I do something to change it so that it looks simpler? And I can answer the question right away. When you think about all your math study, it's always like that. Transform a difficult problem into small pieces so that you can use simple technique to deal with it. Gaussian elimination. Look at the system, how can you solve it? Reduce it to row echelon form, true? Right? So, can I apply certain transformation so that determining whether it can be decomposed become an easy task? So we answer this question, okay, all right, so you apply all kinds of tricks to change the system, but you do not want to change the system so that after you change it, you can decompose it, but originally you cannot decompose it. Useless, right? I can change everything to 0. Oh, I know how to do the 0 matrix. Very happy. But it has nothing to do with the original matrix. Useless. So what kinds of transformation do not change the entangled state or the separable state? Separable meaning that you can do the decomposition. Entangled state meaning that you cannot do the decomposition. It turns out that it's very natural. The thing you can do is that turn out that if the transformation will do the job, the transformation is basically putting A back to A, B back to B by a standard, this is a standard transformation on quantum state. Okay? The nicest invertible transformation. Okay? I will not make too much comment about that, but in physics, if anything change of state space and any transformation allowed, this would be the one. If even this is not allowed, your lab can do nothing. Okay? So apply unitary to it, or apply unitary and then do transpose. So for the first system, I have two quantum systems. I want it, okay, so, wait, take this one. This result says that if you have two quantum states, all you can do is that put A back to A, B back to B, with some change of state space or transposition. Very natural. Or if you are dealing with a situation that the two quantum states are identical, in this case, the dimensions are the same, then you can swap the two things. Those are the only operations you can do. Don't do anything drastic in your lab if you want to maintain the separability or entanglement state. Right. So actually, the physics is, I'm not very happy. That is the only thing we can do, but at least it settles the question. No wild operation you can do for this one. Or you can go back to our result, like the singular value, keeping the picture. We have a corresponding result. If you want to maintain, if you just want to maintain the tensor state, the k sum of k singular value, all right? This time it's not all the same. Well, actually, if it maintain all this, it will maintain all the singular value, but not the k one. But adding the first k one, you get the T fan k norm, something in the major theory called the T fan k norm. And if you want to keep this, again, basically, you can have to maintain the two systems by a big change of basis, UV, to mess it up. But intrinsically, AB still go back to AB. Or AB go to AB transpose, or go to A transpose B, or A transpose B transpose. So that's very limited thing you can do intrinsically, even though superficially, you multiply UV, change the state space for the large dimension gap. Okay, I know this the class will end here. I just want to reiterate, this is an interesting project. No end, you can do tensor decomposition, you can do matrix tensor decomposition, you can do transformation of matrices or the tensor matrices, tons and tons of results and questions available. You have to leave, understand, you can come to my office, talk to me, if you are interested to know more about that. No commitment, I just tell you other things if you're interested in knowing. Otherwise, we'll let you go for the next class. Okay, thank you. You want to stay and ask questions, stay, otherwise go to your class, I know. Yeah, run.